This is part 1 of lecture 1.3 of Math 108, Logical Equivalence. In this video, we will define the concept of logical equivalence and learn how to determine if two propositional forms are logically equivalent or not using truth tables. Two propositional forms are said to be logically equivalent if and only if their truth tables are the same. That is, P and Q are equivalent if and only if P and Q have the same truth value for any combination of truth values of the variables in P and in Q. We use a triple horizontal bar to denote equivalence. Consider the propositional forms P implies Q and not Q implies P. P implies Q is false if and only if P is true and Q is false. It is true for all other cases. Not Q and not P have truth values which are opposite those of P and of Q. Not Q implies not P is false exactly when not Q is true and not P is false. That is, it is false exactly when P is true and Q is false. It is true for all other cases. We see that the columns for P implies Q and not Q implies not P are identical. This means that for any combination of truth values of P and of Q, the statements P implies Q and not Q implies not P have the same truth value. Thus, P implies Q and not Q implies not P are logically equivalent. In other words, a conditional sentence is equivalent to its contrapositive. Now let us consider P implies Q and Q implies P. P implies Q is false if and only if P is true and Q is false, and is true for all other cases. Q implies P is false if and only if Q is true and P is false, and is true for all other cases. We see that the truth values of P implies Q and Q implies P differ in the second and third rows. That is, when P is true and Q is false, and when P is false and Q is true, the statements P implies Q and Q implies P have different truth values. Thus, P implies Q and Q implies P are not logically equivalent. Hence, a conditional sentence is not equivalent to its converse. To illustrate, let P be the proposition 0 divided by 0 equals 1, and let Q be the proposition 1 plus 1 equals 2. The statement P implies Q is if 0 divided by 0 equals 1, then 1 plus 1 equals 2. Its contrapositive is if 1 plus 1 is not equal to 2, then 0 divided by 0 is not equal to 1. These two statements are logically equivalent. The statement Q implies P is if 1 plus 1 equals 2, then 0 divided by 0 equals 1. Its contrapositive is if 0 divided by 0 is not equal to 1, then 1 plus 1 is not equal to 2. These two statements are logically equivalent. None of the first two statements is equivalent to any of the last two statements. In this next example, we show using truth tables that the propositional forms either not P or both P and not Q, not P or not Q, and P implies not Q are logically equivalent. The truth values of not P and of not Q are the opposite of the truth values of P and of Q, respectively. P and not Q is true if and only if P is true and not Q is true. It is false for all other cases. Either not P or both P and not Q is false if and only if not P is false and P and not Q is false. It is true for all other cases. Not P or not Q is false if and only if not P is false and not Q is false. It is true for all other cases. P implies Q is false if and only if P is true and not Q is false. It is true for all other cases. we see that the columns of either not P or both P and not Q, not P or not Q, and P implies not Q are identical. Thus, these three propositional forms are logically equivalent. Knowing which propositional forms are logically equivalent enables us to state a specific proposition in different ways. To illustrate, let P be the proposition 29 is prime, and let Q be the proposition the principal square root of 16 is negative 4. The sentence, either 29 is not prime, or 29 is prime and the principal square root of 16 is not equal to negative 4, is the proposition either not P or both P and not Q. This is logically equivalent to the sentence, either 29 is not prime or the principal square root of 16 is not equal to negative 4, which is the proposition not P or not Q. And to the sentence, if 29 is prime, then the square root of 16 is not equal to negative 4, which is the proposition P implies not Q. You have come to the end of part 1 of lecture 1.3. Before you proceed to part 2, you are strongly encouraged to answer the exercises included at the end of these slides. Thank you for your attention.